Welcome back, everybody. This lesson we're going to talk about two variable inequalities, and I'm going to show you quite a few different examples in terms of two variable inequalities and their graphs and what effect they have on points and so forth. First off, we're going to test to see which of these five ordered pairs make the inequality true. The inequality is negative 2x plus y greater than or equal to negative 4. Tell you what, let's start off, let's choose D. Let's just see if D works. The first coordinate is an x coordinate, 0. Negative 5 will go in for y. So testing it out, negative 2 times 0 minus 5. We want to see, is that greater than or equal to negative 4? Well, anything times 0 is 0. And then we just have quantity negative 5, is that greater than or equal to negative 4? And it is not true. So negative 5 is not greater than or equal to negative 4, therefore D doesn't work. Let's try C. This time we're going to put a 1 in for x. Negative 2 times 1 then is the negative 2. Put a negative 2 in for y, making this a minus 2, and is that greater than or equal to negative 4? Negative 2 minus 2 is negative 4. Negative 4 is greater than or equal to itself. So C works. Now let's check out B. Putting a 0 in for x. 2 times 0 is 0. A 1 in for y. Greater than or equal to negative 4. And then basically we're asking, is 1 greater than or equal to negative 4? And it is. B also works. Trying A here. Negative 1 in for y, in for x. Negative 1 times negative 2 is a positive 2. Plus 1, 1 in for y. Is that greater than or equal to 4? 2 plus 1 is 3. 3 greater than or equal to 4. Oh, I'm sorry, negative 4. Negative 4. Don't forget that negative sign, and that makes it true. And lastly, let's check E down here. 3 times negative 2 is a negative 6. 6 minus 1 greater than or equal to negative 4. All right, negative 6 minus 1, negative 7. Greater than or equal to negative 4. That is incorrect. That's a false statement. So in this problem, A, B, and C, these three make this inequality true. So when you're finding inequalities and solutions, there's a whole range of values. All right, next up, we're going to look at Desmos, the Desmos graphing calculator for. We're going to graph the inequality y less than 1 minus 2x. Let's have a look at Desmos here. Desmos.com/calculator y less than 1 minus 2x. Notice how it graphs. We'll zoom in a little bit to see all the points. Crosses the y-axis at 1, has a downward slope, a dashed line, and the reason for that is that it's a less than, not a less than or equal to. Say I make that a less than or equal to symbol. Whoops. Here, trying to make this a less than or equal to symbol. We can pull up the keyboard down here if you're at Desmos. Here's less than or equal to. Notice it makes it a solid line. Notice it makes it a solid line. Yeah, I mean, our original problem was just a less than. And since it's y is by itself here, when y is by itself, less than refers to shading down. All these coordinate points below the line satisfy the inequality and make it true. All the points outside of the shaded area do not make it true. So this is how this graph looks. All right, let's look at another one here. This time we're going to graph y less than 3x minus 2. Y is less than 3x minus 2. Go back to Desmos and look at that. There we go. All right, so this sort of has slope-intercept form, where a y-intercept is negative 2, and if we look at the graph here, it's crossing down here at negative 2. Slope of 3 as a fraction, 3 over 1. To get to another point on the line, I would go up 3 to the right 1. less than, y less than, saying any point less than below the line is going to make the inequality true. And also notice less than symbol, dashed line, dashed line. All right, let's look at, this time we're going to look at 2 at the same time, known as a system of inequalities. Y less than 2x plus 3, y greater than negative 2x minus 3. Back to Desmos here. We had y less than 2x plus 3. There's that one, and notice you can graph as many as you need. Y greater than negative 2x minus 3. Notice there's a crisscross here where the shadings intersect. The solution to the system is where the 2 shadings, we have this green shading and this purple shading here in this bluish region. All this region here satisfies both inequalities. Notice they're both less than, greater than, not later, less than, equal to, not greater than or equal to. So no dashed, there's no solid line, only dashed lines. But this is in fact the region that would satisfy both inequalities at once. All right, let's kind of look at another system here. This time y greater than or equal to 1/2 x plus 1, y greater than negative x minus 2. Let's see how that looks on Desmos. I'll delete the previous 2. All right, y, and I'm going to bring up the keyboard here to get the greater than or equal to symbol. And then I'm going to do 1/2 x plus 1. So there's the first inequality. Here's the second one, y greater than negative x minus 2. All right, we see the point of intersection. The point of intersection is not really considered in the solution. This dark shaded region, including the line, the solid line. Any point on this line here, this region here, not down here, but right here, makes the inequality true. And we can see where the 2 shadings crisscross. And that is the solution to the system. All right, now we're going to look at another one where we're given the graph and we have to come up with the system on our own. What's the system of linear inequalities shown from the graph? All right, well, we'll just look at one at a time. We'll look at this dashed line here in blue. All right, notice that it crosses the y-axis at -2, and looks like to go from one point to another, I'm going like that, a -2, not a -4. I go down 1, right 1. Notice that. Down 1 and to the right 1. All right, that's a -1x. All right, and since we're shading underneath the line, and it's a dashed line, I need y less than -1x minus 2. Yeah, and just keep in mind what I'm using here. I'm using mx plus b, the slope-intercept form of a line, to make these inequalities. That's kind of the model I'm using. I think this other one here I'll do in red. This line here looks like it's crossing the y-axis at 1, +1. And to go from one dot to another, looks like another crisscross happens there, up 2 and right 1. That would make a +2/1 or just +2. The shading here is happening above the line in question, greater than, and then there's our system. All right, now the next one is sort of what we call a linear programming problem. It says Danielle can spend up to $600 buying small and large jackets for employees. Small jackets are $20 each, large jackets are $25 each. To get a special discount, she needs the number of large jackets to be no more than twice the number of small jackets. Also, she needs to order at least 6 small jackets and 10 large jackets. The graph shows the feasible region where x is the number of small jackets, y represents the number of large jackets. Which ordered pair meets all the constraints and makes in the sense of the context of the situation. So all these lines here graphed are describing the situation here. She can spend up to $600, the cost of each one, and the vertical and horizontal line are the constraints of how many she can buy. At least 6 and 10 large. Okay, notice we have the y-axis, y horizontal line here 10, vertical line here 6. That represents that. As long as she has combinations of large and small that fall into the constraints here, we're good to go. So let's go through each one and check. 10, 13 here. Let's go to 10 and then up to 13. There it is. So that one definitely works. Let's try 7, 15. Here's 7. 15 would be outside of the shaded region, so that one does not work. Let's try 13, 11. Right, 13 and up to 11. That's right here. Notice we are inside the shaded region, so C works. D, 8, 9. Here's 8, and here's 9. 8, 9, outside of the region. That's not going to work. And then finally, we have E is 15, 11. Let's get a different color here, purple. Here's 15, here's 11, right there. Alright, so A works, C works, and E. Those combinations of large and small jackets are within the constraints, within the shaded region, so we know it satisfies the constraints. Alright, and then this one's a little different. It says Sheila needs to bring at least 25 pieces of fruit to training practice. She suggested apples and oranges. Was told to be sure to bring more than 10 apples. Let X represent the number of apples, Y represent the number of oranges, which inequalities model the situation. Okay, so at least, we see the phrase at least. Now, even though it has the word least in it, when you see at least, it means go with greater than or equal to. So X and Y, apples and oranges combined, have to be greater than or equal to 25. B satisfies that. If you add them together, they're at least 25. 25 and up, greater than or equal to 25. Alright, and she needs to bring more than 10 apples. More than 10 apples. X is the number of apples. C, if you're greater than, you are more than. So we still have the number of oranges. As long as, could be all oranges, could be 0 oranges, could be some combination thereof. But because we really don't have a constraint, as long as she is greater than or equal to 0, that would represent the number of oranges. See, on the situation, at least 10 apples, but they don't say how many apples, at least 10. Could be all 25 as apples. That would encompass 0 down here for the number of oranges. And then we have one more situation to talk about and see if we can find the inequalities that work here. Theater manager is planning an upcoming concert. Regular tickets cost $12, student tickets $8. The theater can seat at most 200 people. The manager wants to collect at least 1,000 from ticket sales. X is the number of regular tickets, Y is the number of student tickets. Which inequalities are among the constraints? Alright, the theater can seat at most. Now we see at most. When you see the phrase at most, contrarily thinking, it's less than or equal to. We're looking for that inequality. Less than or equal to 200, that's the most they can sit. C in the theater, X plus Y less than or equal to. Now, we need an inequality. It has 12X and 8Y. X is the regular tickets, and Y is the student tickets. So we're looking for one of these down here, C, D, or E, and then we have the phrase at least. So for at least, we're looking for greater than or equal to. Alright, so we see at least $1,000. We want greater than or equal to. That would go with C here, 12X plus 8Y, greater than or equal to $1,000. Alright, so that is a few examples talking about two variable inequalities, systems of inequalities, and also applications. Thank you for watching.